Hello everyone, and welcome back to another video. Today we have a nice integral from Maths 505. You should definitely check him out and his approach. We're going to be using a slightly different one today, one that relies on series expansion and the rest. But when I actually first saw this integral, I plugged it into Desmos, as one does, and I thought, oh, well, yes, this is just, it's like 0.690, whatever. I'm like, oh, yeah, that's just the natural log of 2, because, Desmos does rounding errors and things like that. But actually, it's not equal to the natural log of 2. Just for reference, this is just like 0.693. So I'm like, okay, 3,000, that's reasonable. But it's actually not, which is quite interesting. So it's a number very close to that, but different. So anyway, a little tidbit there that threw me for a loop. Because I was assuming this whole time, it's like, oh, it's the natural log of 2, let me prove it. And lo and behold, it's not. So yeah, anyway, to the actual integration, we're just going to let u equal the negative natural log of x. And then you just, do u sub stuff. Nothing too interesting here. We end up getting the integral from 0 to infinity of e to the minus x. These x's are different. I'm just, I'll use u, I suppose. Times the sign of the square root of u du. Prove that for yourself if you'd like, but just take my word for it. The focus of this video isn't on u subs, it's on, other things. So what we're going to do now, then, is just express sine in terms of its Taylor series. So what we're going to have, then, is the integral still from 0 to infinity, but of e to the minus u times the sum from k equals 0 to infinity of, u to the 2k plus 1 over 2, because of that square root right there, times negative 1 to the k over 2k plus 1 factorial. And just kind of rearranging this right here, what we end up getting actually is just the sum from k equals 0 to infinity, negative 1 to the k over 2k plus 1 factorial times the integral from 0 to infinity of e to the minus u times u to the 2k plus 1 over 2. This is a mouthful, but trust me, it simplifies, because this right here is nothing but 2k plus 1 over 2 factorial. You recognize that as just like the gamma function of like x plus 1. So using this, that was a lot and quite fast, but using this, we can simplify this quite a bit to just being the sum from k equals 0 to infinity of negative 1 to the k, but then times 2k plus 1 over 2 factorial times 2k plus 1 factorial. And to solve this, we're going to use another kind of obscure gamma function identity. This just comes from the duplication formula, actually, so it's not that obscure. But continuing the trend in the videos over the last day or so of using weird gamma function tricks, it follows from the duplication formula, actually, that gamma of z over gamma of 2z is equal to, I'll full screen this bit right here. Gamma of z over gamma of 2z is just 2 to the 1 minus 2z times square root of pi over gamma of z plus 1/2. And when originally doing this, I kind of forgot to convert between the gammas and the factorials. So to do that, it's actually not that bad, because we're just going to multiply by z and then 2z here to convert, meaning that the z's actually just cancel. So to get, this is the same as if we were just to add like a 2 there. And now this works for, factorial, so instead these are now factorials. Pardon the notation, but I think the point remains. Basically that z factorial, so z factorial over 2z factorial. Sorry, those z's wouldn't cancel, these on this side would cancel. I'm sorry, but you get the point. Z factorial over 2, goodness me, I'm writing k already, okay. Z factorial over 2z factorial is just equal to 2 to the 1 minus 2z times the square root of pi over 2 times the gamma of z plus 1/2. So yeah, that's just what we're going to be using. I cannot write today. So using this, we know then that our z is then just equal to 2k plus 1 over 2, meaning that whenever we plug everything in, what we're left with here is just, 2 to the 1 minus 2k minus 1. I'm just going to put the square root of pi over 2 out front. over gamma. Well, what's gamma of z plus a half? Well, that's just going to be gamma of 2k plus 2 over 2. But, you know, all the 2's cancel, meaning that we're left with here, and simplifying the numerator as well, what we're left with is just the square root of pi over 2 times 2 to the minus 2k over gamma of k plus 1. So subbing this back into our original equation, or summation, I suppose, what we're left with is the sum from k equals 0 to infinity of negative 1 to the k. I'll put the square root of pi over 2 out front here, square root of pi over 2, times 4 to the negative k, I'm simplifying a little bit, over k factorial. And you'll notice here that actually this looks maybe a bit familiar if I write it this way. So square root of pi over 2 on the outside still, but then we have the sum of negative 1/4 to the k times 1 over k factorial. And you'll realize that this right here is nothing but the power series just for e to the x, meaning that what we actually have is nothing but e to the minus 1/4 times the square root of pi, I cannot write pi today, pi over 2. And that right here is really just the answer. This is just our integral right here. So yeah, this is kind of a shorter video, short and sweet, but hope you all still enjoyed and are liking the random gamma function identities. And yeah, see you on the next one. Thank you for watching.